Science time. Today's objective is you're going to write down describe waves. So I'm going to write it over here. Describe waves. The title, what would be a good title for this lesson, do you reckon?
Waves.
Waves. Let's title it Waves. Waves. Okay, so a second ago we were reading through the unit opener, and Andrew said something that was, she read something about waves that we really want to focus on, and that is that waves have, as everything in the universe has, waves have properties. So when I say properties, what does that mean? Does that mean they own land and crop and the rest of it? Yeah, okay, so properties are something that is true about a certain entity, a certain physical thing, right? So what are some properties of Leo?
He has hair.
Hair. He has hair.
Yeah.
How would you describe his hair? Brown. Brown, short, right? His hair, some properties of Leo's hair are brown, comma, short, right? So we're going to talk about properties of waves. What are some properties of peas? Like the things we eat. What are some properties of peas? Green, round. Yeah, I just want to make sure you understand what properties are. What are some properties of the whiteboard? White.
It's a
Whiteboard. No. What are some properties of this?
Smooth.
Shiny.
It has a certain what? Are there any parts that we could measure?
Size.
It's what? Size. Yeah, we can measure the area it covers. What else?
Magnetic.
Yeah, we can measure its magnetic field. What else can we measure about the whiteboard? We can measure its volume. Yeah, we can measure how much space it takes up. We can measure its mass. We can measure. There's lots of things. Really, anything about an object or a entity that you measure is some kind of property out there. But we're going to be talking about today the properties of waves. And from our properties of waves and from a list of waves that we generate, we're going to think of one. Our goal today is to think of a general definition that's true of all waves, and I'll help you out with it, so don't get too afraid. And also, don't cheat by looking in the book, and they have the definition there for you, but don't look at that yet. Justice. So, what are some properties that waves have? I mean, when you think about any kind of wave, what are some properties that it has?
You can't see it.
Not always true, because you can see water waves, can't you?
Yeah. Water waves.
What are some properties of waves? What makes? Okay, here's a little example. My son, who's 5 months old. Yeah, 5. I don't know. I was trying to look at the day. He is 5 months old. My son, who's 5 months old, has a little sound machine that helps him go to sleep, and it has a wave on the sound machine. Like, it'll make the sound of a wave. Why is that relaxing? What's true about waves?
I don't know.
What? Make the sound of a wave right now.
Whoosh. Well, and certain waves can be like relaxing in a way.
Yeah, but why?
Because it's so
Because
calm.
both of you, the words,
It's
the
natural
little
to get calm.
the little noise that you made is not actually describing waves. I'd say that's more like the whoosh. If you were to do the waves, how would you make that sound with your mouth?
Wah, 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 wah.
Okay, you're getting closer. You're getting closer because waves have to do what?
Go.
It's relaxing and
Make noise.
it
Bounces.
I agree that
not all those things are true
it
for all
like
waves.
makes a wavy.
Yeah, if we were to draw a wave, it does what?
Move. Goes up and down.
I do the
and up
same
and
thing
down and up and down.
Several times. If I'm making the sound of a wave,
That's like straight.
right? It
That's
has to
like
be.
straight.
There has to be more than one because it does what? Colton.
Moves.
No, not necessarily. Well, we'll get there in a second, but yes.
I was gonna say it's consistent and has multiple.
Yeah, and we call that, it does what?
Repetition.
Yes, it repeats. So, properties of waves. Waves must repeat. Repeats. I'm going to try to spell repeat correctly. Repeats. Waves repeat. Waves have to be repetitious.
Just one wave, and then they.
Yeah, it wouldn't really count as a wave anymore, right? Waves repeat. Someone said, or a second ago, it was you, Cyrus, someone said that they have to be doing what? And this is not, we're talking, yeah. So there has to be some kind of motion. There has to be motion of matter or energy. Let's put that, matter or energy. Something is moving from one end of this wave to the other. And this is we're getting a little ahead of ourselves here, but if this were pretend this is a water wave. Pretend this is a water wave, and we're thinking about just one little particle of the water wave. Or pretend there's a little, like, a bobber, like a fishing bobber, right here on the water wave. How will this bobber move? You know.
Waves. Down, up.
It goes up and down, up and down. It doesn't, in general, it doesn't move from here to here unless there's a current or unless something's pulling it, right? Because just like Newton's first law says, this thing is not going to move left or right unless there's a force acting on it left or right. What force is acting on it up and down?
Water.
Gravity, and then the water pushing it up, right? And so that cycle repeats, and so it does move up and down, but it isn't going to just go left and right on its own, right? If you pull it, it'll go towards you, or if it gets pushed by the wind, it'll move. But in general, when something's on a wave like this, it goes up and down. So the matter is moving. It's moving up and down, but is matter being transferred from here to here? No. What is being transferred from here to here? The bob is just going up and down. The wave is transferring what though? What if it's not transferring matter? It must be transferring
Air.
air's matter,
Stuff.
water's matter.
Stuff.
What doesn't matter?
Energy.
Energy. So the motion of matter or energy. So the matter is moving in this case, just for the water wave. In water, the matter is moving how? Up and down. But the energy is moving from place to place. So this is a water wave. What other kinds of waves are there? I told you I was going to have you ask this question.
Sound.
Types of waves.
Yeah, there's heat waves.
Sound waves. When we say a heat wave, that's a thing that we're talking about, like it's getting real hot outside for a number of days. So that's not a real kind of wave. It feels like a wave because it comes over the landscape and it gets hot in the daytime and then cold at night. So it does repeat and it's a cycle, but it's not a true wave in the sense that we think about waves because it's more like if we were to graph the temperature, that would look like the graph would be a wave. But the heat wave itself is not a wave. So sound waves, we already said water waves. Light waves, what else? Hayden? Did you have a question? What else? What other kinds of waves are there?
Energy.
Micro.
Okay, so energy waves in general, that light waves are a type of energy wave, but really all kinds of waves move this energy, right? All kinds of waves move energy. That'll give you a hint for what your definition is going to be.
Microwave.
Microwave. Microwaves. What else? What other kind of waves can we think of? Are there any? I'll give you a hint. There are more, but this is a fine list for now. There are different kinds of light waves, though. Can you think of other kinds of ultraviolet light? What other kinds of light are there?
LED.
LED is the type of thing that produces light, and what kind of light does that produce?
A brighter light.
Light that we can do what with? Can we see microwaves? You can see a microwave oven, but can you see the actual microwaves that are emitted by it? No. Can you see ultraviolet light?
Yeah. Oh, I mean, no.
No, not really. If you have special goggles or something, you can. Can you see infrared light? No. So what's special about the light emitted by an LED? And this is in fact what we name it. It is called. If we can see it, it must be visible. Visible light. So visible light is a kind of wave. Visible light. And I also mentioned ultraviolet light. I forgot to make this picture-in-picture. There we go. And then I said infrared light. X-rays.
What's the one above infrared?
Ultraviolet. X-rays are a kind of light.
Yeah.
All of these, and then there are more, gamma rays. All these are kind of light waves. What's that? A CAT scan uses waves. And in fact, it detects gamma rays, which are a kind of wave. Let's put gamma rays on here. Gamma rays. So all these ones I have listed down here are kinds of light. Is sound a kind of light?
Yeah.
No?
No.
Oh, no it isn't. Is water a kind of light? No. All of these ones are types of light waves, but the other two are not. So can we think of a definition now that we have these properties of waves, right? It repeats, it must move energy. We have some different types of waves. Can we think of something that is true for all of these that could be a definition of a wave? A wave is what?
Motion of matter.
Okay, the movement of matter.
And energy.
Movement of, let's put energy instead. The movement of energy, or, it's just saying or. Movement of energy through matter, or through, if it's not moving through matter, how could it move?
Energy.
Well,
I mean,
it is the movement of energy, but if it's not moving through matter, it's moving through what instead? If there's no matter, we call that
light.
No. We said it earlier. If there's no matter, like in outer space, it's called a. Remember the word I used? A
Vacuum.
vacuum. Thanks, Cyrus. Yeah, through a vacuum. Make sure you spell it right. Vacuum is spelled V-A-C-U-U-M. As far as I know, it's the only word in English language that has two U's, or two U's in a row. Movement of energy through matter or through a vacuum. In a, how could we describe the way it moves?
Fluid.
What is our other? What else must be true about a wave? Yeah. Well, we can't say moving as a wave because that's what we're defining as wave. But it does what? A wave must repeat. In a
Fluid motion.
no. In a you use the word you just said. In a repeating. What do we call it when something repeats?
Repetition.
Yeah, but a repeating
Pattern.
pattern. Good. Repeating pattern. You know about patterns, right? You did in math when you were in like first grade. You had like triangle, circle, triangle, circle, triangle, circle. What's the next one in order, right? It's the same way here. We have names for these. I'm going to tell you. Crest, trough, crest, trough, crest, trough, crest, trough, crest. What's going to come next?
Trough.
Trough. Yeah. So it's the same thing. It's a repeating pattern. So it's a movement of energy through matter or through a vacuum in a repeating pattern. Do you think a water wave can move through a vacuum? No, it's got to have water, right? And water is matter. Can a sound wave, we talked about this, can a sound wave move through a vacuum? No. Can light waves move through a vacuum? Yes, they can. So it doesn't always it's not always able to move through a vacuum. Can light travel through matter? Well, yeah, I mean, you can see the sunlight, right? And that's traveling through the air, which is matter. But can the light travel through that wall? No. So can it always travel through all matter? No. So it's not always through all matter, and it's not always through a vacuum, but it has to be traveling through one of those things, right? Yeah. So a wave is the movement of energy through matter or through a vacuum in a repeating pattern. These things, any kind of matter that the wave travels through or the vacuum is called the wave's, what we call the medium. Medium. Write it down. The medium that the wave is moving through is what it's moving through, right? So what's the medium of the wave carrying our bobber here? What's it moving through?
A medium.
Water.
Yeah.
Water. What's the medium? What's the medium of the light waves coming from the ceiling light allowing you to see me?
Light.
No. What's the medium? What's it moving through? Air. In that case, right? What's the medium of the sunlight going from the sun to planet Earth?
Space.
Yeah, a vacuum.
Vacuum. Yeah.
Vacuum. So what the wave is moving through is called the medium. Write that down. The medium is what we call the entity. Let's put the stuff. Let's just put stuff. The stuff the wave is moving through, right? A vacuum is not really stuff, but there's not really a good word for any kind of matter or a vacuum. We have two more things that I want to talk about. The first is that waves have properties, right? They repeat and they move energy, but they also have what we call anatomy. You know what anatomy means?
Anatomy.
What's anatomy? When we're talking about the anatomy of the human, body, we're talking about what?
The body.
Like the body. Oh, bless you. No, well, not necessarily. Not for anatomy.
Body parts.
About the body parts. So if we were talking about the anatomy of a wave, we would be talking about the what of the wave? The parts of the wave. So I'm going to erase this diagram. I'm going to erase our little properties of waves up here.
No.
And I'm going to draw a diagram of a wave. So this will be true for all waves, but there's a couple different kinds of waves that we're going to talk about in a second. So this is a diagram of what we call a longitudinal wave.
And then there's like smaller ones.
This is called a longitudinal wave. This is one of the two types of waves. The two broad, instead of saying types, I should say categories of waves. So the longitudinal wave what's true about a longitudinal wave is that the energy flows perpendicular to particle, or let's put to matter movement. The energy flows, so which way in this, you know, what could this be a drawing of? A picture of a what?
A sound wave.
Nope, not a sound wave. It won't work with sound wave for this one, but like a water wave. We'll say a water wave. Energy, we could say, is flowing from here
All the way
to here. So flow of energy. But what direction is the matter moving?
To the right or right.
No.
Think about the bobber. If there's a bobber up here, which way is the up and down?
Up and down.
Up and down. So the flow of matter, or we'll just say the movement of matter, and describing the movement of matter relative to the flow of energy, which is right and left, how are those two things related? You know about math? Like, if one thing is up and down and the other thing is right and left, they are perpendicular, just like I wrote, right? So in a longitudinal wave, energy flows one way, and the matter moves in the opposite direction, perpendicular to it. Okay, and for a longitudinal wave, we name the parts of it this. This is called a crest. The top is called a crest. How can you, I don't know, you know about crest. Like the crest of a mountain is the top of the mountain, right?
Yeah.
The bottom part is called the trough. Like a pig trough is a hollowed out thing, right? You with me so far? Crest is the top of a wave. The trough is the bottom of the wave. This thing here is called, sometimes it's called the origin, sometimes it's called the baseline. This dotted line, and that's like the average height of the wave. So some parts of the wave are higher than that, some parts of the wave are lower than that, but on average they're all about medium level. Do you see what I mean? Mm-hmm. So the baseline is like the average height of the wave. The amplitude of the wave is the height from baseline to crest or baseline to trough. These two things are both called amplitude. The height of the wave is called the amplitude. They should be the same. This height should be the same as this one. The wavelength is the distance from one crest to the next crest.
Wait, the height of the wave is what?
The amplitude. And then the wavelength is the distance from one crest to the next crest, or one trough to the next trough. That's the wavelength. So far, so good?
Yep.
And the last thing is, if we think about this wave in motion, right, instead of just a picture, how many of these crests or how many troughs pass by in a certain second is called the frequency. The frequency is how many crests or troughs pass by in a unit of time. So a high frequency wave would be moving how compared to a low frequency wave? Faster. A high frequency wave would be moving faster. It'd have more of them pass in a certain amount of time. For something called a transverse wave, which is the other kind of wave, fiddlesticks. Listen, hey, write this down before you go, okay? All this stuff is the same except the compressions are places where the matter is close together. Instead of a crest, it has a compression. And the rarefactions are places where the matter is far apart. And so instead of troughs, it has rarefactions. Okay, and that's called a transverse wave. Have a great rest of your day. Oh, your assignment is to do exploration 1 by tomorrow. Have a good day.